Hello and welcome back. Today we're going to be taking a look at actual measurements. Before, we were able to hear the various sounds when we were inserting capacitors into our simple circuit with the button, and we are listening to the sound of the voltage using this piezo buzzer. So remember, when we have no capacitor in the circuit, we have nice, crisp, clear sounds. And I've got the oscilloscope hooked up so we can actually see the traces. And when we let go of the button, you see that we get a nice, crisp, clear decrease in the sound. So what we'll do now is we'll put in various capacitors. And remember that we have the 10, the 100, and the 470 microfarad capacitors. In the last video, I think I said 470 micro ohm. This is a 470 microfarad. All of the capacitors are measured in farads. So we put in the 10 microfarad capacitor into our circuit, and we are placing this across the load. Now, a lot of times our load is a resistor, but our load is going to be the buzzer here, the piezo buzzer. And so now when we tap out the dots and dashes, we hear it nice, crisp, and clear. And on the previous video I said, well, we can't hear that, we can't detect it with our ears, and it sounds much like it sounded before. But when we take a look at this on the trace, we'll start to see that there's a slight difference. So we turn on the buzzer, and we let it go. And you see how we have a very sharp transition, but it's not a vertical one. So even though we can't really hear that when we listen to it, we can see that there's a slight transition. So there is exponential decay. It's just too quick for our ears to hear. So what we can do is we'll get a single shot, and then we see that there's a slight exponential decay. And it's hard to see from the graph exactly how fast that decay is, so we can use the horizontal zoom on the display, and we can move this to a convenient position, and then we can zoom in on that decay. Now we're really zoomed in. If we take a look at the scale on the bottom here, we see that each of these divisions is going to be 40 microseconds. And so when we look at this, we see, well, how much does it take to get to 1 over E, which is roughly 1/3 of the value. When we look, how far does it take, how long does it take to get to about 1/3 of the value? Well, it's hard to tell, maybe a little bit more than one division, but we can see that the time constant of this circuit is roughly, or on the order of 40 milliseconds. Now, one of the rules of thumb that I use is, well, it's hard for us to divide by 2.7 in our head. So if we're just looking to get a sense of the time constant, 1 over E is 1 over 2.718, but for we humans, it's nice to just think of it as 1/3. And I realize that's a pretty rough approximation, but if we're just looking to get a sense, 1/3 is a reasonable value to look for. So we can say how long does it take to get to be 1/3 of its value? Well, you can ballpark it right about here, which is about 40 milliseconds. So 40 milliseconds is too much for our ears to hear, but if we zoom in, we can use the scope to measure that time constant. All right, so let's get us back to where we were before. And we can look for that. And if we are to look at dots and dashes, we still get the full transition down to 0 for each of the transitions. But even though we can't hear it, we do see that there's a slight delay in the falling time of the voltage. So now let's take out our 10 microfarad And now that we have increased the capacitance by a factor of 10, that time constant should also increase by a factor of 10. Let's listen to it first. And so that's very noticeable to our ears. And if we were trying to tap out a message in Morse code, we would see that we have difficulty distinguishing it by sound. Now let's see what happens. And when we look at it on the graph, we can see that there's a much more distinct decay, because as we have that falling edge, the capacitor is discharging. And if we tap out, we see that if we go quickly in our dots and dashes, we don't even reach the zero value, and that's why they're getting smeared together. So our ears can detect that smearing, but it's on the scope we can measure it, and we can also see that we don't even get to the zero voltage condition when we tap out quick dots and dashes. So let's do a single shot here. Okay, I'm going to zoom in a little bit, and we're going to do, and that'll grab just that one. And now we would be able to measure the fall time, and again we want to see how long does it take for the capacitor to discharge to 1/3 of its original value. So it starts up here and it discharges. How long does it take? So we're going to zoom in here a little bit, and now when we do similar, so we look and we say, how long does it take? We have to look at our time division, and our time division here is 200 milliseconds. So we'd say, how long does it take to get to 1/3 of its value? Well, about 1/3 of this would be about right here. Let's call it right here, and that would mean there's 2 divisions, each of which is 200 milliseconds. So it would take about 400 milliseconds for the capacitor to discharge to 1/3 of its original value. And that makes a lot of sense, because in the previous value, for the previous 10 microfarad capacitor, it was 40 microseconds, and here we've seen that it's about 400. Before it was 40 milliseconds. Here it's about 400 milliseconds, which is a factor of 10, which, when we take a look at the factor here, the capacitance goes up by a factor of 10, and the amount of time that it takes to fall to 1/3 of its value, which we call the time constant, is also upped by a factor of 10. And here we can measure it. All right, well, we'll go for the BFC here, the big fat capacitor for 400 microfarads. Now that we've got the big fat capacitor in here, remember how we could barely discern dots and dashes. And let's look at it on the scope. And we can really see that fall time now. And it would allow us to measure it. You can hear the voltage decay, and now with the scope we can see it decay. And it takes a long time for the buzzer to finally shut off and to decay, and that's the reason why it would be difficult to do any Morse code with this button and this buzzer with the capacitor in it, because everything just kind of gets smeared together. So it's hard for our ears to hear, and we can see that the reason is that we don't have a distinct rise and fall between each of those. So with this, I'm going to take a single shot, and now we can analyze it. And when we look at this, it's going to be harder to see. But if we take a look at this point here, we'll move it a little bit. So this is the transition period, and we'll look down, and we see now each of the horizontal divisions is 400 milliseconds. So how many divisions does it take to get to about 1/3 of its value? Well, let's see, here's about 1/3 right here. So we'll call that 1/e. And so it takes all of this time, which we'll call 1, 2, 3, 4, 4 time divisions. So that would be 1.6 seconds, 1600 milliseconds. So the fall time here is about 1.6 seconds. And if we think about the time constant as being the time at which we can distinctly determine a couple of pulses, that means every dot or dash would have to have at least 1.6 milliseconds in between it in order to have a clear and distinct signal. So this is one way that we can measure the time constant. And the whole reason I wanted to show you this was because in your lab, you're going to be seeing traces. You're going to be seeing square waves on the simulator, and you always want to be able to liken that to some sort of physical phenomenon, and in this case, we've translated it to sound. So when you're seeing the square wave on the simulator and circuit lab, you'll be able to correlate it with a physical phenomenon.